Okay, let's jump right into this explainer because we are going to totally demystify the foundational physics of X-rays. We'll trace their, honestly, fascinating accidental discovery and then explore the rigorous safety protocols used in modern medicine. If you've ever looked at a medical scan and wondered exactly how it works at a molecular level, well, you're in the right place. We're going to break down the absolute essential concepts of radiologic science, starting straight from the fundamental laws of physics. Here is our roadmap for today. 1. Matter and energy. 2. Sources of ionizing radiation. 3. The discovery of X-rays. 4. The evolution of medical imaging. And finally, 5. Basic radiation protection. Let's kick things off right at the beginning.
Section 1. Matter and Energy. The universe's building blocks.
To really understand the nature of our surroundings, we first have to establish the basic rules of the universe. And honestly, it's pretty simple at its core. Absolutely everything around you can be classified as either matter or energy. Matter is basically anything that occupies space and has mass, the physical substance built from atoms. Energy, on the other hand, is simply the ability to do work. A moving car has kinetic energy, a pot of boiling water has thermal energy. And more often than not, matter and energy exist right side by side. But here's where it gets really interesting. Thanks to Albert Einstein's theory of relativity, we know that matter and energy are actually interchangeable. You definitely know the equation E equals mc squared. Energy equals mass times the velocity of light squared. This incredibly simple but profound relationship means matter can literally be transformed into energy and vice versa. It's the absolute foundation for nuclear power and modern nuclear medicine. Section 2. Sources of ionizing radiation, the invisible forces. So when energy is transferred through space, we call that radiation. Visible light, that's radiation. But in radiologic science, we rely on a much more powerful type called ionizing radiation. Here's exactly how it works. Ionizing radiation, like X-rays, packs enough energy to knock an orbital electron completely out of its atom. It just ejects it right out of there. This creates what's called an ion pair. The ejected electron becomes a negative ion, and the remaining atom, now missing an electron, becomes a positive ion. This highly specific ability to ionize matter is exactly what gives X-rays their unique medical power and, of course, their potential hazard. Now, you might think this ionizing process is confined to a heavily shielded hospital room, but we are actually exposed to it constantly. Radiation exposure is measured in millisieverts, or MSV, and it's pretty wild how our exposure is split. It's almost perfectly even. We get about 3 millisieverts annually from completely natural environmental sources, things like cosmic rays, the Earth itself, and radon gas. On the flip side, we get about 3.2 millisieverts annually from man-made radiation, and that's almost entirely derived from medical imaging. Section 3. Discovery of X-rays. A happy accident. So, with these incredibly intense physical forces at play, how did humanity finally figure out how to harness them? If I asked you how X-rays were developed, you'd probably assume some brilliant team of scientists spent decades engineering a massive machine in a top-secret lab, right? Well, the surprising truth is that they weren't developed at all. They were discovered completely by accident. Back in 1895, a physicist named Wilhelm Röntgen was just experimenting in his laboratory. He was studying the conduction of cathode rays through a partially evacuated glass tube known as a Crookes tube. Right in the middle of his experiment, he noticed a nearby material, barium platinocyanide, started to glow, or luminesce. He hadn't engineered anything new. He had simply stumbled upon a completely unknown, invisible form of penetrating radiation. And he didn't waste any time. Within weeks of this accidental discovery, Röntgen investigated this new radiation with unbelievable scientific vigor. By early 1896, he published this historic, somewhat eerie, but absolutely fascinating first medical X-ray. It's an image of his wife's hand. If you look closely, you can clearly see the dense, dark ring on her finger completely blocking the rays compared to the somewhat transparent bones. This single image proved the immense, immediate value of his discovery to medicine, and it eventually earned Röntgen the very first Nobel Prize in Physics in 1901. Section 4. Evolution of medical imaging, looking inside. From that single grainy image of a hand, the entire field rapidly evolved. We started with Röntgen in 1895. Fast forward to the 1950s, and a light amplifier tube was adapted for fluoroscopy, which suddenly allowed for dynamic, moving images like watching a live broadcast inside the body. Then the 1970s brought us computed tomography, or CT scans. By the 1980s, MRI became an accepted modality. Today, we're in an era where advanced digital radiography allows for incredibly precise diagnoses on high-resolution displays. It has been an incredibly fast journey.
Section 5. Basic Radiation Protection, Harnessing Power Safely.
Of course, with this incredible power to look straight through the human body comes the absolute responsibility to protect patients and medical personnel from those hazards we talked about earlier. Modern radiology relies heavily on 5 core safety features. Those are filtration, collimation, protective apparel, gonadal shielding, and protective barriers. Let's look a little closer at how a few of these actually work in everyday practice. First up is filtration. This is perhaps the most important patient protection characteristic of any imaging system. Typically, state statutes require general-purpose units to have a minimum total filtration of 2.5 millimeters of aluminum inserted right into the X-ray beam's path. Now, why aluminum? Well, it efficiently absorbs weak, low-energy X-rays before they ever even reach the patient. Those low-energy rays wouldn't contribute anything to a useful medical image anyway. They would literally just increase the patient's radiation dose for no reason. So, increasing filtration actually increases the overall quality of the X-ray beam while keeping you safe. Next is collimation. Simply put, collimation ensures the X-ray beam is strictly confined to the specific body part being examined. By narrowing the beam, you completely avoid irradiating adjacent healthy tissue. But here's the really cool part. Beyond just protecting the patient, collimation drastically reduces harmful scatter radiation, and reducing that scatter actually improves the contrast and clarity of the final image. So it's truly a win-win. And to ground all this in your own experience, think about those heavy lead aprons you wear at the dentist, or the lead-lined boots the technologist stands safely behind. These are mandatory protective barriers. For example, the fluoroscopic image receptor assembly itself serves as a primary protective barrier, and that requires the equivalent of 2 millimeters of lead. This carefully engineered shielding is exactly why personnel radiation exposure today is kept incredibly low. Which brings us right back to our starting point. How do the universe's most basic building blocks let us safely see inside ourselves? Well, by understanding the theoretical interchangeability of matter and energy, and by learning exactly how ionizing radiation interacts with our atoms, we've mastered the ability to illuminate the human body. From an accidental glow in a 19th century lab to the advanced digital scans we have today, radiologic science is a massive triumph of human curiosity. It leaves us with one pretty provocative question. As our understanding of physics deepens, what invisible forces will we discover and harness for medicine next? Thanks so much for exploring this explainer with me today.